Hello, good morning to all of you. We know the magnetic field produced due to the current length element is given by the Biot-Savart law. The magnetic field due to the current element at a point is given by the relation dB is equal to mu 0 upon 4 pi ideal sine theta upon r square, where theta is the angle between the current element that we see here. Suppose this is the current element and here this is the point. Then theta is the angle between current element and the line joining from center of the element to the point. Ideal is current length element here. And r is the distance of the point from the current element or center of this current element here. Now we have to see the applications of Biot-Savart law. The magnetic field produced due to the long straight wire carrying the current can be calculated by using the Biot-Savart law. Consider an infinitely long straight wire carrying the current I in the direction as shown in this figure here that we have seen here. Now consider the point P at a distance, at a perpendicular distance r from the wire, that is from the point O. Let the current element ideal at a distance L from the point O. The point P is at a distance r from the current length element here. Now the magnetic field at point P due to this current length element is given by dB is equal to mu 0 upon 4 pi into ideal sine theta upon r square. dB is equal to mu 0 upon 4 pi into ideal sine theta upon r square. The direction of this magnetic field is perpendicular to the plane of the figure and directed inward. That is, it is directed into the plane of the figure here. The total magnetic field at point P due to the entire wire is the contribution of magnetic field due to all such current length elements in the upper half of the wire. And this can be obtained by integrating this equation. We can call it as equation number 1. Integrating this equation 1 between the limits L is equal to 0 to L is equal to infinity. We can obtain the magnetic field due to the all such current elements in the upper half of the wire. The contribution is also due to all such current length elements in lower half of the wire. In both the cases, the direction of magnetic field is same, that is directed into the plane of the paper, and hence the total magnetic field at point P due to the entire wire. The total magnetic field at point P due to the entire wire is given by B is equal to twice the integral of dB, integration limit between 0 to infinity here. And hence we write here B is equal to twice integral of mu 0 upon 4 pi ideal sine theta upon r square. Integration limit is from 0 to infinity. and it is equal to now from figure R is equal to sorry, 1 minute. We can take this constant term mu 0 upon 4 pi out of the integration. That's why we write here twice mu 0 upon 4 pi integral of ideal sine theta upon r square. Integration limit 0 to infinity here. Now suppose this is our equation number 2. But here r is equal to under root of L square plus r square. That we have seen in our figure, that is that we can re-diagram here. That is, this is capital R, this one is L, and this one is R. Now here we have considered this angle is theta, and that's why this angle is also of theta. This is pi, this angle is of pi minus theta here. We can by applying the Pythagoras, we can write here r square is equal to L square plus r square, and hence r is equal to under root of L square plus r square. Further, sine of theta, that is equal to sine of pi minus theta, and from this figure sine pi minus theta is equal to r upon r here, and hence we get here equation number 2 as, that is putting this equation 3 and 4 in equation 2, we get B is equal to mu 0 upon mu 0 I. I is also constant, therefore we can take it out of integration sign. Mu 0 I upon 2 pi integral of r dl upon L square plus r square bracket raised to 3 by 2. Integration between 0 to infinity here. Or we write here mu 0 I r upon 2 pi integral of dl upon L square plus r square bracket raised to 3 by 2. Integration limit 0 to infinity. And let us suppose this is our equation number 5. Equation number 5. Now we can solve this integration then. Integral of dl upon L square plus r square bracket raised to 3 by 2. As usual, integration limit is 0 to infinity. Again, from the figure, we can write L is equal to r tan theta. Therefore, dl is equal to r sec square theta d theta. And hence, or also we can change the limits here. We have the earlier limits are L is equal to 0 to L is equal to infinity. That is when L is equal to 0, that means tan theta is equal to 0 because r cannot be 0, and hence theta is equal to 0 here. And when L is equal to infinity, that is L is equal to infinity, in that case tan theta is equal to infinity, and therefore theta is equal to pi by 2, and hence the integration limit changes as theta is equal to 0 to theta is equal to pi by 2, and hence we can write here integral of dl upon L square plus r square bracket raised to 3 by 2, integration limit 0 to infinity here, that is equal to, now change, we can put L as in terms of theta, and hence we get integral of r sec square theta d theta upon r cube in bracket 1 plus tan square theta bracket raised to 3 by 2. Integration limit is 0 to pi by 2 here. Now here this term in the denominator as occurs because we put L is equal to r tan theta, and that's why if we solve this term, that is L square means r square tan square theta plus r square, and this bracket raised to 3 by 2 here. R square is taken as a common factor here. R square we have taken as a common, and in bracket we write here tan square theta plus 1, and square bracket raised to 3 by 2. Now we can remove the square bracket, that means r square raised to 3 by 2, that gives us r cube, and hence finally we get here this term as r cube in bracket tan square theta plus 1, tan square theta plus 1, and hence we write here in the denominator r cube in bracket 1 plus tan square theta bracket raised to 3 by 2 here, and further it is equal to, that is equal to 1 upon r square integral of cos square theta raised to 3 by 2 sec square theta upon sin square theta plus cos square theta bracket raised to 3 by 2. We just modified these statements. Here, one of the r is get cancelled, the 1 upon r square that we have get here. Sec square theta means cos 1 upon cos square theta. Tan square theta can be written as sin square theta upon cos square theta. By following that terms, we get directly this as 1 upon r square integral of cos square theta raised to 3 by 2 sec square theta d theta upon sin square theta plus cos square theta bracket raised to 3 by 2. Now then further, if we solve here this term as 1 upon r square integration limit 0 to pi by 2 is here. We have left cos theta d theta because sin square theta plus cos square theta, that is 1. And here for cos square theta raised to 3 by 2, that gives us cos cube theta, that is equal to cos cube theta, and hence we write here cos cube theta into sec square theta, that is 1 upon cos square theta, and hence this cos square theta get cancelled, and in the denominator we have left only cos theta here and d theta here, and that's why finally the integral will be equal to 1 upon r square integral of cos theta d theta 0 to pi by 2. We know the integral of cos theta d theta, that is sin theta, and hence we write sin theta limit between limit 0 to pi by 2. Here sin pi by 2 is 1 and sin 0 0, and that's why finally we get 1 upon r square. The integral value will becomes 1 upon r square. Put this value in equation number 5. In our equation 5, we have put it, that is b is equal to mu 0 ir upon 2 pi into 1 upon r square. And hence finally the magnetic field due to this long straight conductor is given by the relation B is equal to mu 0 I upon 2 pi r. Mu 0 I upon 2 pi r. R is the distance of the point from the conductor and I is the current flowing through the conductor or wire. Now then, we can calculate the force between the current carrying wires. Consider two current carrying wires which are parallel to each other that we have shown here. Consider two long parallel current carrying wires separated by the distance d. These two wires are designated. Suppose here this is wire 1 and here another wire 2 here. Both the wires are separated by the distance d here. We know current carrying wire produces the magnetic field around it. And that's why the current flowing through the first wire, that is I1, produces the magnetic field on the wire 2. It produces the magnetic field at a point that we have considered here, this point, and which is given as B1 is equal to mu 0 I1 upon 2 pi d, as we have just earlier seen it. B1 is equal to mu 0 I1 upon 2 pi d. Now, this second conductor then, or second wire, which is carrying the current, is under the influence of the magnetic field. According to Lorentz force, the force acting on the second wire due to the magnetic field B1 produced by the current I1 flowing through the first wire is given by B2 is equal to I2 B1 integral of D1. We consider the small part of the length as dl, and hence we considered here total integral, that is total length of the wire then. Therefore, the force acting on it, according to our usual relation, force acting on the current carrying wire is given by F is equal to ILB sine theta. But see here, the magnetic field B1 has the direction perpendicular to the plane of the figure and directed inward, that is into the plane of the figure here. And that's why theta is equal to 90 degree. Sin 90 is 1. Sin 90 becomes 1, and hence we get here ILB. I is the current, L is length of the conductor, and B is magnetic field. And hence the force acting on the second conductor is F2 is equal to I2, which is current flowing through it, B1, the magnetic field produced due to I1, and integral of dl, that is total length of the wire. Now this force is given as also I2 is equal to, by putting the value of B1, that is F2 is equal to I2 mu 0 I1 upon 2 pi d. That is we have put the value of B1. And that is we write here mu 0 I1 I2 upon 2 pi d integral of dl. This force is directed towards the first wire. The force is directed towards the first wire. And therefore the force per unit length, the force per unit length acting on this second wire is given by the relation F is equal to mu 0 I1 I2 upon 2 pi d. Mu 0 I1 I2 upon 2 pi d. Now, similarly, In the same way, the force per unit length acting on the first wire is also mu 0 I1 I2 upon 2 pi d, and which is directed towards the second conductor. That is, here we can consider this is F1. Force per unit length acting on both the conductors is same, have the same magnitude, but their directions are opposite, as we have seen here. And therefore, these two wires attract to each other. These two wires attract to each other. That is, if the two currents are parallel to each other, that is, the currents are flowing in the same direction, in that case, these wires attract to each other. Thus, we can draw here the conclusion. Thus, the two parallel conductors attract each other when the currents flowing through them are in the same direction. And if the currents are anti-parallel, that if the currents are in opposite directions, then they repel to each other. That is, we write two parallel conductors repel each other when the currents flowing through them are in opposite directions. If the currents are in the same direction, the conductors attract to each other. If the currents are in opposite directions, then the conductors repel to each other. Thank you. We can now stop here.